Okay, let's check the audio and the video. Are the audio and the video good? Can you hear me? The audio and the video good? Let me see. Um, Here's my. Yeah. Oh, one second. Let me just re-log into the Zoom because I think something goes wrong. Yeah. 1. Oh, okay. Can you help me to locate my, yeah, is my mouse in the correct place? Okay, here we go. All right, got it. Okay, thank you. Yeah, sorry. Let me see. The last time audio, okay. So I will take a look at the Zoom recording of the last time later. Let's go ahead to share my screen right now. Sorry, sometimes the Zoom picture. Okay, all right. Okay. All right. About the last lecture, I have uploaded the Zoom recording to the playlist. And regarding the audio thing, I will take a look and get back to you as soon as possible. So I will check it later. Yes, it is in the play listing now. Okay. All right. Sorry, something wrong with the Zoom. Stay as co-host. All right. So let's go to. All right. So I have printed out the homework 5. So let's take a look at the problem in homework 5, and meanwhile, let's review what the definitions and concepts we have learned last time. So let me get the homework 5 ready, which is 15, homework 15, okay. That is this. And 15. Okay, all right, so let's get started. Let's see. Okay. All right, so let me fix the Zoom recording for the last time later. So let's start with the review of section 17, and let's go ahead to use some problems in homework 15 to review what we have learned last. Okay, good. All right. So what we learned is the definition of continuity. So before starting, let's just take a look at think about question, think about warm-up question. So we use y equal to this. How about that? Y equal to 1 over x. We took this one, the example last week, right? Last time, okay? So we call the definition of continuity at a point. We call the definition of continuity of point on an interval and so on and so forth. For this function, if I write out the function without specifying what x could be, it means that I just take the natural domain as a domain, right? So for this function, the domain of the function is all real numbers except 0, right? No problem. Okay, the question, think about that. Is this function continuous? According to our definition, is this function continuous? Okay, take a moment to think about that. This function defined for all real numbers except 0. Is this a continuous function? Not continuous, because what?
It's not continuous every row in its domain. Well, I'm saying that wrong. It's not continuous all over the real numbers, or maybe I'm saying that wrong again. Because of a 0, that's like a
Jump, right?
A jump.
An infinite jump. Yes, it's very obvious that at 0 we have an infinite jump, right? But is 0, the number, does 0 belong to a domain? No, 0 does not belong to a domain, right? So it has some problem at 0, but 0 does not belong to a domain, right? That's the second, let's recall the definition. Definition is that to define, okay, there are 3 levels. First of all, we define that, okay, to define the function, definition to define a function of a continuous. How to define that as a continuous? By definition, we mean that f is continuous at each point on its domain. That's definition. We see the function continuous is the function continuous at each point on its domain, right? The domain is all real numbers except 0. So 0 does not belong to the domain, right? Because the function not defined as 0. So at any non-zero real number, 1, -1, 2, -1, half, whatever, at any non-zero real number, is this function continuous? Let's think about that. The graph of function looks like that. It might look like that. And the domain gonna be all real numbers except 0, right? That's domain. All real numbers except 0, right? So when we see whether or not function is continuous, we just see whether or not function is continuous at each point on its domain, right? zero does not belong, so we don't care what's happening at zero, because zero does not belong to the domain, right? So let's rethink this one. Using the definition, do you feel like this function is continuous or not? So according to our formal definition of a continuous function, this function, it is continuous. Because it is continuous at each point on its domain. So you wonder, okay, this one seems like there's a jump. Yes, there is a jump, but at the point zero, zero does not belong to the domain, right? So compare this one with that one. I have another function, the y equal to 1x, the y equal to g of x. This function I defined as 1x when x is 1, 0, and I define it as whatever value, 1 or 2 or 3 when x is 0. So what's the domain for this function? The g of x, the domain is all real numbers because it's defined everywhere, right? When x is non-zero equal to 1x, when x equal 0 defined equal to 1. If this function, according to the definition, this function, the g of x, is this continuous function because what? Because even though it's continuous at any non-zero point, but it is discontinuous at a zero. Here, 0 does belong to the domain of all real numbers, right? 0 does, the graph looks like that. If you just get the graph of G looks like that. You have this, and then this. See here? At 0 equal to 1. But when you are approaching to 0 from right, goes to infinity. If you approach 0 from left, goes negative infinity, it's not consistent, right? So that's why this function g of x is discontinuous 0. If it's discontinuous at any point at one point, then we see that that's discontinuous function. But on the other hand, for this function, it is defined only at non-zero real numbers, only defined at 0. So 0 does not belong to the domain. In this case, 0 does not belong to the domain. So we don't care what's happening at 0, right? So the function, if you compare the two functions side by side, the y equal to 1x using the natural domain, that one is a continuous function. But for the y equal to g of x, this one makes it more clear. For the first one, y equal to alpha of x equal to 1x. For alpha of x, it is discontinuous on the natural domain. And for g of x, alpha of x continues on the natural domain, g of x is discontinuous on the natural domain. So here is the domain is very important, okay? So your domain is very important. You have to take a look at function first, then take a look at what's the natural domain of the function. Okay, so that's kind of something we learned. Okay, all right. So be careful with this one. For example, in calculus 1 or calculus 2, when we talk about the 1 over x, we say, okay, there's a jump at 0. So kind of like that by default, you consider g of x and f of x, right? Okay, all right, so come back here and take a look at the first example as we try to apply the definition to prove that the function sort of x is continuous on its domain, 0 to infinity using the sequential definition, okay? So here to prove something is continuous, we have two approaches. Number one is the sequential definition, number two, it is the absolute definition, right? So here let's recall how to prove a function is continuous on its own. So here number one, method to define a function is continuous. And here, to prove level one, to prove a function y equals to alpha is continuous. We need to show by the definition, first of all, we need to show alpha is continuous at each point in the domain. Does make sense? That's definition. So basically, to prove that function is continuous, that is, you need to show that for any x in the domain of x, F is continuous at X. To prove a function is continuous, basically you have to show for all X from the domain of F, the function is continuous at this X. Kind of like to show that, for instance, to show that all of the IC students are happy, you have to show for all IC students. Pick up anyone, arbitrary one, right? Their student is happy, right? And then that's a for all type statement. All right, so how to do that? That's definition. To prove such kind of like for all statement, remember structure? To prove a for all statement, what should we do? That's the definition, okay? To prove such kind of for all statement, what should we do? That's a direct proof. Okay, so remember something we have learned at the beginning of semester to prove such a for all statement. Step one, we should take up an arbitrary X, right? To prove that for all IC students, we are happy, or to prove for all IC students, they have taken 3326. To prove something is true for all, just pick up an arbitrary element from the group, right? Without nothing special, right? Just pick up something at random. Told you I pick up something at random, right? So step one, we're going to take X as an take X, which is a real number from domain. So domain is 0 to infinity. You have told that that's the next domain. So domain is here. That's the domain. Domain of F is 0 to infinity. So just pick up the arbitrary point from the domain, right? Pick up X is nothing but a non-negative real number. Nothing special about that. Just a not real number which is greater than equal to 0. Okay, and we should do something. So here it's kind of like to prove it, just the set of steps, step 3, step 4, and so on and so forth. Finally, step 5, you have to show that F is continuous at X, right? Pick up an arbitrary point from the domain and do something. Finally, if you can arrive at the conclusion that and it's continuous at the point, then what? Then we can see that F is continuous on the domain, which is 0 to infinity. Right? That's kind of the structure. That's structure, right? So here, how to fill out the detail, that's something you should think about, but that's not structure, right? So how to show that F is continuous at one X? Here we have two approaches. You can either use the definition, another definition. Here you are told to use the sequential definition. Let's recall the sequential. Here, basically, you can justify the epsilon, this details, this difference. Basically, you can try the sequential definition, or you can try the epsilon third definition. Generally, you have two ways to go, but in this case, you are told to apply the sequential definition. You only have one way to go, right? But generally, if it's not specifying which method to apply, you can do two. There are two ways to go. So sequential definition, what's the sequential definition? As we call the sequential definition is the sequential definition going to be for all sequential definition. Okay, we call the sequential definition. This is nothing but for all sequences Xn, which is in the domain, and Xn converging to X. Okay, for all sequences from domain, such that it's converging to X, we need to show f of X and converging to f of X. So sequential definition is also for all type statements. So you should show that for all sequences, Xn can be any sequence from the domain. As long as Xn is converging to X, you will show f of Xn converging to f of X. That is again for all statements. So to show that one, so the sub kind of like sub cases. So I want to see one point. I just want to do 1.1 gonna be take Xn as an arbitrary sequence from the domain Xn, X1, X2, X3, whatever. There are so many real numbers from 0 to infinity, right? And then that's 1.1, 1.2, what you're gonna do is assume that limit of x n equal to x. So that's a condition. Condition is let x n is convergent to x, right? And your conclusion, so do something. Your final conclusion is to show the limit of f of x n equal to f of x. Okay, that's the key point. Assume this, your goal is to show this. If you can do that, you are done. That makes sense? So, because that's for all type statement, so take an arbitrary sequence xn and assume the condition to assume xn convergent to x, show limit of f of x convergent to f of x, right? The structure here. Then how to prove that? Let's see, what is f of x? This one is nothing but limit of, what is f of x? Come back here, f of x is nothing but square root of x, right? F of x is square root of x. In this case, the f of x is square root of x and f of x is square root of x and f of x is square root of x. So they are the same. To show this, you need to show this, right? Just plug in because f of x is square root of x. So f of x is square root of x. And what's the condition you have? The condition you have is this is nothing but limit of x n equal to x. Let's see here. Is this true or not? If the limit of x equal to x, do we have limit of the square root of x equal to the square root of x? Do we have this? In terms of here, well, the advantage of using the sequence definition is you can make use of some kind of theorem you have learned of sequences and theories in section 12, section 13, section 14, and so on and so forth, right? If you know limit of x equal to x, so you know the limit of x square root of x equals square root of x. So basically, this one can be rewritten as you need to show the limit of n goes to the limit of square root of x and equal to square root of limit of x. So basically, x here we know that x is nothing but limit of x. Do we know the limit of square root of xn equals square root of limit of xn? Is this true? Limit of square root of xn equal to square root of limit of xn. Do we have such kind of result? Here the xn is convergent, right? Is the limit of square root of xn equal to square root of limit of xn? So that is something you can verify. Okay, so here to verify that, check some theory of the properties we have learned in the previous section for sequences. Or I can give you a hint. Remember there we have something like the limit of n squared equal to the limit of this. Remember this one, limit of product equal to product limits, right? Remember this one? Right, we have talked about this one many times. So similarly, we have a similar one. Limit of square root equals square root of limit. Limit of the square equal to the square of limit. This kind of thing they are both true. But to show this true, you have to find the theorem, find the propositions in section maybe 13 or 11 or 12, I cannot remember. Find out and cite because of proposition, because of theorem, we have this. So that's true. Okay, so that structure. Structure is the kind of take x as an arbitrary non-negative real number and prove x continuous at 0. To prove that x continuous at x, you will use the sequential definition. And in the sequential definition, to apply sequential definition, take up arbitrary sequence. Assume the limit of x equal to x. Prove the limit of f of x equal to f of x. Because the advantage of using the sequential definition is most of the times to fill out detail, to fill out this gap from here to here, to fill out this gap. Basically, you do not have to prove it from scratch by yourself. On the other hand, here to fill out this gap, you can try to apply some theorem you have learned about sequences to fill out the gap. Okay, so just like that's what kind of like we are learning sequences, property of sequences, and then we are learning continuous function. The theorem we have learned about sequence can be applied here. Because of something we have learned. So we get this. Okay, so that's kind of structured. And I'm gonna stop here. That's number one. Okay, number two, let's see. Number two is epsilon and delta definition. So here we have applied the sequential definition. Let's take a look at the epsilon delta definition. So here, same thing, same kind of problem. Alpha x equal to square root of x. We need to use the epsilon delta definition to show that f is continuous at x naught. Here x naught equal to 0. Okay, let's see. What do you show? You need to show f is continuous at x naught equal to 0 using the epsilon delta definition. Okay, so you don't need to show f is continuous, you only need to show f is continuous at 0. Okay, x naught is 0. You only show it's continuous at this one point using the epsilon delta definition. Okay, so that's it. So what's the epsilon delta definition? Here to apply the epsilon delta definition, the sample is given. So here, let's recall what's the epsilon delta definition. To show that a function is continuous at a point using the epsilon delta definition, here is that's the epsilon delta definition for functions to be continuous at a point, which is for all epsilon, right? Again, that's for type statement. You should find the delta, there exists delta, right? Find the delta such that for all x in the domain, here the natural domain is R. In this case, for y equal to x squared, natural domain is R. For x in R, such that when x minus x naught is very small, less than delta, we have f x minus f of 2 is also very small, less than x. That's the epsilon delta definition. Okay, all right. So here to show this one, so the key point is you have to take up or select a delta. Remember, because that this structure is very similar to show the definition, to show limit of some sequence equal to a number. Use the definition, right? For any epsilon over there, you have to find the n, capital N, such that something is true. Here is for any epsilon, you have to find the delta such that for active domain something is true, right? Very similar structure. In this, a little bit more complicated, but very similar thing. For any epsilon, step one, pick up a arbitrary epsilon. Step one is here, step one. Pick up the arbitrary epsilon because that is for all type statements. So step two, you have to choose the delta. So here you don't know why delta is chosen to be the minimum of one common epsilon of 5. Delta is chosen to be this number because of some brainstorming, or remember we have to do some brainstorming, some algebra ahead of time, right? And then we can select the delta and then write it out. Okay, choose the delta such that when the condition is x minus 2, absolute x minus 2 less than delta, and eventually you have to show that when this is true, you have to show this is true. When x minus 2, absolute x minus less than delta, we have to show f of x minus f of 2, absolute less than x. Makes sense? So the structure is very similar to something you did before. Show the limit of sequence equal to a number. Here we just show the function continuous at this point, right? Okay, so given this, come back here. This is kind of proof structure. First of all, specify the natural domain of the function, and then that's kind of step 0. Step 0, step 1. Take up the epsilon delta, step 2, choose your delta, and then finally, to do that. Finally, if you show this is true, then you're done. Understand? Structure is given. So you mean how to choose the delta? To choose the delta, we have to do some brainstorming before proof writing. Okay, brainstorming part. The brainstorming part comes from here. How to do the brainstorming? That's a key point. The goal is to show f of x minus f of 0 less than epsilon from here. We try to, from here, try to solve for delta. Remember the function to find capital N. We start from the inequality, solve for capital N. Same thing here, we start from this final inequality and try to solve for delta. Okay, what is this final inequality? F of x minus f of 0. The x value is nothing but, in this special case, f of x is square root of x minus f of 0 is nothing but 0. Because f square root of x is 0, okay? So this is nothing but square root of x. Square root of x is always non-negative, so we can get rid of the epsilon, right? The inequality to show this is less than epsilon, take a look at that. We need to show the square root of x to be less than epsilon, then your x should be this one, meaning that to show this, we only to show x is less than epsilon squared. You agree? Algebra, right? In order to show the square root of x less than epsilon, x should be less than epsilon squared. But remember, you may want to here, how about x negative? So x should be non-negative because the domain, in order to make sure that x is domain, so x by default is a non-negative number. Yes.
So would it be the minimum of 0 and epsilon squared?
Okay, so that's a good question. First of all, delta by default, let's take a look at that. So by default, delta is a positive number, right? Positive number. So let's see, given this one, how to choose the delta? So you're saying that to delta with the minimum of
0 and epsilon squared?
let's see, 0 and so let's see what's wrong with this.
Okay.
If you choose delta to be the minimum of 0 common epsilon squared, so let's see. What is 0 and epsilon squared? Which one is smaller? 0 is always smaller, right? If you write down something like minimum of 0 common epsilon squared, this is nothing but 0, right? The 0 is always smaller than epsilon squared, right? So, and the delta here, remember delta should always be positive. Delta cannot be negative. Delta, just like epsilon, can always be positive. This one is not good choice, but we can modify this, kind of give us a direction. How about let's choose delta to be epsilon squared? Let's find out. First of all, find some candidate to serve as delta. If the candidate doesn't work, then modify it, right? Not big deal. And it's not big deal. So just like we just try it. The first attempt may be correct, maybe not. If your first attempt is not correct, doesn't matter. Try it out again, right? So let's try here. If you try to choose the minimum of 0 common epsilon squared, this one won't work. Obvious, right? So let's choose delta to be epsilon squared. So how about this one? Can this one work? Let's verify it. If you choose delta to be epsilon squared, let's try to see if we can get it from the top to the bottom. So let's see verification. Just write down the proof here. So first of all, specify the structure. Okay, step 0, okay, the domain, the natural domain of f(x) equal to square root of x is pretty important to specify the domain, right? The domain for this function is, what's the domain?
0 to infinity.
0 to infinity, including 0, right? That's no problem. Okay, then step 1, take epsilon as an arbitrary positive real number, right? Because that's a whole type statement. Step 2, let's choose delta to be epsilon squared. So because epsilon is positive, epsilon squared is positive, so here delta is also positive, okay? Then step 3, let's try to verify that when we need to verify if assume, right? Okay, let's take up. So what we need to show that for any epsilon, okay, remember this one definition. For all epsilon definition that for all epsilon, there is with delta such that for all x in the domain, we need to show when x minus 0 less than delta, we need to show alpha of x minus alpha of 0 less than epsilon. So you can, if you're not quite sure of, if you're not quite familiar with the definition, you can write down definition side by side. Okay, so right now we have done this. We picked up an epsilon. We have done this. We already chose a delta, right? Then what's that? Step three gonna be, what we're gonna do later is step three is gonna pick up for all kind of, for any x from the domain. Okay, pick up the arbitrary x from the domain. The domain is 0 to infinity, so pick up x from 0 to infinity, right? Then assume x minus 0 less than delta. Okay, that's the condition. Condition conclusion if P and Q, right? If P and Q to assume P is true. So assume x minus 0 less than delta. Okay, so let's see. Assume this. So let's see. If x minus 0 less than delta, that is x less than epsilon squared. Because you chose delta to be epsilon squared. If epsilon of x less than delta, then we know that x is less than epsilon squared. That makes sense? And that is x less than epsilon squared. Because what? Because you know that x is always non-negative. If x is always non-negative, you can get rid of the epsilon sign, right? That makes sense? So we are able to get this. This one is just because of that. And we are able to get this because of that. There's reason behind it, okay? All right, so because of that, then what? We know this, and basically we know x is gonna be 0. So x is between 0 and square root of x, so we have the square root of x less than x. Yes? That's just algebra, right? X is non-zero, non-negative, and less than epsilon, so square root of x is gonna be less than x less than epsilon squared, the square root of x is gonna be less than epsilon, right? That is, okay, that is half of x less than epsilon. Because square root of x equal to f of x. The reason behind it is square root of x, f of x equal to square root of x, right? Equal to just the replacement. And that is f of x minus f of 0 less than epsilon, because f of 0 equal to 0, right? And finally, that is square root of f of x minus f of 0 less than epsilon. Why we are able to add the square root? Because f of x equal to square root of x is always non-negative. For non-negative real number, we can feel free to, for non-negative real number, with or without the epsilon sign, they are the same, right? That's it. So we are able to do that. Okay, let's step backward to take a look. Pick up a arbitrary epsilon for the delta chosen to be epsilon squared. We are able to show that for any x in the domain at once, or when x minus 0 less than delta, we can show that f of x minus f0 less than that. Right then. So by the definition, as a summary, finally we have summary. We have shown so far, we have shown that for any epsilon, there exists delta which is epsilon squared, such that for x from the domain of f, as long as x minus 0 is less than delta, we know f of x minus f of 0 less than f. We are done. The summary is here. Okay, the summary is what we have done so far. That's it. Okay, the brainstorming part is you have to do the brainstorming ahead of time. So to find out what your delta should be, right? To solve for delta, to take a look at the final inequality. Most of the time, you are able to solve for delta from the final inequality, right? Once you know the candidate for your delta, then you can try to write out the formal proof. If you got stuck somewhere when you're writing the formal proof, if you got stuck, same like, okay, I'm not able to arrive at alpha x minus alpha 0 less than epsilon. If you got stuck anywhere when you do the proof writing, modify the choice of the modify it until it can go through. All right, and if you recall this process, like brainstorming, do the brainstorming solve data from the inequality, then write the proofs from the top to the bottom. This procedure is very similar to the thing you did before, prove the limit of sequence equal to a number. The only difference is over there for sequences, you have to find the capital N, right? But here you have to find the data. That's the only difference. But other than the structure, gonna be very similar. Okay, so if you want to, if you need more help, you can take a look at the writings given in the template 2A. The 2A proof is given. We can modify or try to make use of the same structure to write out the proof of 2B. 2B, they are very similar. Okay, all right. So let's see. And similarly, the C is gonna be another one. It's a little bit complicated because what? Because your fx, first of all, fx piecewise defined function. The natural domain is all real numbers. So think about that. Let's do the brainstorming part. Your key point here is for C. For C. First of all, brainstorming, you have to solve for data from this inequality, right? This inequality is nothing but f of x minus f0 less than delta. So what is x? What is f of x? For x in the domain and x minus 0 less than delta to show that. So think about that. How to do this? This is a brainstorm. So here, first of all, you have to think out what is f of x. But the f of x is a piecewise defined function of two pieces, right? So basically, to show this one, you would have to consider two pieces because there are two pieces. Your x here, your x from the domain, and x is very close to 0. From the definition, let's see here, x is domain. Domain is all real numbers. Your x is any arbitrary real number, and x minus 0 is very small. From those two definitions, x can be any real number, like it could be 0, could be non-zero, like 0.1, 0.2, and so on and so forth, right? So x can be any real number, so you have to consider two cases. Case one, if x equals 0, and case two, if x is non-zero. Why do you need to consider two cases? That's a piecewise defined function, right? If x equals 0, then your f of x is just 0. In this special case, f of x minus f of 0 is nothing but 0. 0 for sure is less than any epsilon. Then the trivial case, right? The trivial case. And in case two, when x non-zero, in this case, f of x equal to x and sine of 1 over x. When x is not 0, f of x equal to x times sine 1 over x. So in this case, f of x minus f of 0 equals to f squared of x sine of 1 minus x. You need to require this to be less than x. Okay. So in this case, you have to pick up from here, you can solve for the delta. Here, basically, in this case, any delta could work. Because no matter what the delta is, 0 is always less than epsilon. This is the identity, forever true, right? Forever true. You do not need to restrict delta to be anything. Delta can be anything. No, delta is free. No restriction, right? In any circumference, 0 is always less than epsilon. Done, right? So no restriction. But for this case, how to make sure that this is less than epsilon? So here you want to get sine function, sine of 1 over x. How can I solve this inequality? How can I solve x? Remember the trick, the transitivity, A less than B, B less than C. Remember, you're gonna apply the trick again. So here, this is the x times sine of 1 over x. If you want this one to be less than epsilon, here, your hope A less than C. The key point is you can find a B. If A is less than B and B is less than C, then A less than C, right? Transitivity. So what is your B? The x sine of 1 over x. This is less than equal to, do you agree that? Yes, because sine function is always between 1 and 1, right? Sine function is always between 1 and 2, so that's, so here we can choose your B to be the f squared of x. From here, you only need to require delta to be absolute. As long as delta is absolute, then it works. If delta is absolute, then when x absolute x less than absolute, then absolute x less than delta, right? And then the x times sine 1 by x less than absolute, then that's it. So here you can choose your delta to be just absolute. Here's the domain R. This is the brainstorming chart, but I just want to bring out, if you have piecewise defined function, if f is defined in two different ways, using two different formulas, so basically you have to split it into two cases, case one and case two. So even though you have two cases, exactly, but the first case is always trivial. You just write it out. Okay, case one is just like trivial case, right? It's super obvious. There's nothing you need to do, but just write it out. Okay, and then for the case two, again, the transitivity A less than B, B less than C, then A. Okay, again, prove the following function is discontinuous at the indicated points. You can use either the sequence definition or the absolute definition. So here it's about the negation. We have learned the definition of function in continuous. So what's the definition of function in discontinuous? Let's see, where sequential and absolute. Okay, let's recall the definition. What's the definition for function? Let's see. F x is continuous. F x not. By the sequential definition, you see f x is in this one. We do that f of x is continuous. X not also is in the domain, right? So we have two definitions, the sequential definition and the absolute definition. What's the sequential definition? I recall the definition again. The sequential definition should be for all sequences from the domain of the F. Okay, all sequences from domain of F. If the limit of xn equals to x, if the limit of xn equals to x, then the limit of f of xn equals to f of x. So for all xn, p of xn implies q of xn, right? That's p of xn. That is q of xn, right? All right, so what's the negation? What's the negation that f of x is discontinuous at x naught? In other words, how to negate the green part? The green part is the continuity. What's the negation of the continuity? What's the negation? The negation of this gonna be, what's the negation of for type statements? For isolated, we are happy the negation gonna be
If P, then not Q.
there exists.
Oh, yeah.
First of all, there exists one sequence from the domain such that T and not to mean a limit of f of x and is different from f of x. That's a symbolic form for to see that function discontinuous at zero using the sequential definition, right? Negation, there exists a sequence such that P and not Q. Okay. So here basically it's going to be easier to show something discontinuous at zero using the sequential definition, because using the sequential definition, you only need to find one sequence, such that this is true and this is not true, then you're done. Right? That's gonna be easy. Okay, but to make it complete, let's recall the definition, absolute definition. What's the absolute delta definition for continuous? Continuous at one, absolute delta is gonna be for any absolute there exists delta such that for all x, if x is in the domain of F and x minus x naught less than delta, this implies f of x minus f of x naught less than x. this is the absolute definition for a function to be continuous at zero. What's the negation? From here, the negation also negated. From here to the negation. How to negate this one? Let's do it one by one. There exists for all becomes there exists, right? And epsilon. Here they give me for all. Here there exists x such that p and not here. P is write down x in the domain, x minus the x naught less than delta, and not q meaning after of fx minus fx naught to be greater than equal to up, because q is less than, non-q can be greater than. Very standard, right? When you say a for all, negation, replace the for all by they exist. When you say they exist, write down for all. When you say for all, write down they exist. If you see p implies q, write down p and not q. That's it. Okay, but you see here, if we try to prove a function discontinuous at x not using negation, using the epsilon delta, it's gonna be very complicated. You have to find the epsilon such that blah blah blah. This is true, which is very complicated. On the other hand, the sequential negation is much easier. You only find epsilon such that this is true. That's much easier than this. Okay, even though you have two choices to go, but when you try to prove something discontinuous at x0 and x at some point, I will recommend you to go by this. This will be much easier than this. And similar, this is also much easier than this, because for sequences, we have learned so many theorems before, right? You can apply inside those theorems. However, if you want to use the epsilon delta definition, you have to create your epsilon delta from scratch, which is more complicated. Okay, so that's a review, and let me see a couple more problems. We can discuss the rest of problem on Friday. So that's